Up to this point in our thermodynamics unit, we have learned that thermodynamics has a goal of being able to predict if a reaction is spontaneous or not. And we learned with the second law of thermodynamics that if the delta S of the universe is positive, then a reaction will be spontaneous. At this point, we have also learned how to calculate the delta S of the surroundings of a system, not the system itself. So in this unit, we're going to describe what's called the third law of thermodynamics, and we're going to recognize factors that affect the magnitude of the entropy of a system. And the entropy of a system can be calculated with the work in this unit. And that's where we'll start. We're going to learn to calculate the delta S of the system, which we're subscripting here with Rxn, meaning reaction, because the system is typically a reaction. We're going to learn to calculate it under standard state conditions, and that is what this little symbol right there means, is that it is under standard state conditions. So if anything is a gas, it'll be at 1 atmosphere. If any substance is in solution, it'll be at 1 molar. So the delta S standard for a reaction would be determined, as is any delta, by final minus initial. Well, the final would be the products, and the initial would be the reactants. So final minus initial. Now this is true for any delta of a state function. It's the final minus initial. When we were dealing with delta H, we couldn't stop there, though, because we can't know the H of the products or the H of the reactants. We had to always talk in terms of delta H. With entropy, that is not the case because of the third law of thermodynamics. Here is the statement of the third law. The entropy of a perfect crystalline substance is 0 at the absolute zero of temperature. Now let's see what we mean by all that. What's a perfect crystalline substance? Well, that's what's being represented over here. Every lattice point has the atom or the molecule perfectly aligned within the structure. There would be no missing pieces or parts within that. It's perfect in every way. And we take that perfect organization and we bring the temperature down and slow those atoms until there's zero movement. Then we would have no disorder whatsoever, and we would have a value of 0 for that. What that enables us to do is have a starting point. This is 0, and as we warm it up, we have an entropy increase, and everything above that is positive. Okay? So we don't have to always talk about changes of entropy. We can talk about the value, the true absolute value, and I don't mean absolute value as in these symbols in mathematics. I'm talking about how much entropy is actually in that substance, and we don't always have to talk about changes. So entropies are always positive. 0 would be no disorder, no randomness, and everything above that would be a positive value. There will be a table provided of entropy values. Make sure you note when you're looking up values whether it's in the solid, liquid, or gas state, because that matters, and whether it's aqueous or gaseous, because that matters. Okay, so let's look at some factors which affect entropy. The first thing we've already talked about. Solids have less entropy than do liquids, and the gases have more entropy of all by a large margin. But here's a couple of other factors. Molar mass. Molar mass, as it increases, will have an increase in entropy. So if you compare two substances and they're both gaseous, for example, the one with the higher molar mass will have more entropy. There's more electrons, there's more movement within those electrons, more disorder. Allotropes. Now, you can't look at an allotrope necessarily and know which one has more entropy than the other, but you ought to realize that the connectivity of those atoms within the substance or within the element makes a difference in the entropy. So here are two phosphorus allotropes, white and red, and we see that they have different values of entropy. Molecular complexity. If you stay within a given state, like all solids or all liquids or all gases, as the molecular complexity increases, the entropy will increase. Well, if we have elemental oxygen here, or we have NO, they have roughly the same molar mass. The O2 is slightly higher, so according to molar mass you would expect, well, maybe it would have a little bit more entropy. The NO has more disorder, has a higher entropy because it is a compound versus the O2, which has less complexity because it is an element. The fifth is dissociation. If you take an ionic compound and you dissolve it in water, it's going to have a higher entropy than the solid state. So here we have sodium chloride as a solid, in which you have nice order of the Na and the Cl and the Na and the Cl and the Na. Whoops, that's a Cl and the Na. So we have this nice straight order of the ionic compound, and it's going to be less disordered than if you dissolve it into water and those ions separate from each other. So when you're looking up values in a table, you'll be looking up values where the solution is 1 molar, and if you need it in solution, you look for the AQ, and if you need the solid sodium chloride, you look for the S because it makes a difference. So this is the end of our learning objective number 6, in which we have looked at the third law of thermodynamics. We've looked at factors that affect the magnitude of entropy, but we have not yet started calculating that delta S of a reaction. That'll be in our next learning objective.